Good afternoon, everyone. Happy Friday. Welcome to the TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience, otherwise the feedback could interfere with the information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Now, without further ado, here's Mr. Carizales for 1314.
Hello, all. Welcome. Thank you again for joining us. I'll give a few seconds for those who are here for the 1324 to go ahead and click on the link that's on the chat for you guys to go and review for the Intro to Business meeting. All right, so for today's session, we're going to go over exponential and logarithmic functions. Okay, so what I like to do is first introduce what an exponential function is. And this is the book definition that you'll find for exponential functions. It says that an exponential function with a base a is denoted by f of x is equal to a to the x power, right? Where the a, it refers to, again, the base, and the x is our exponent, okay? All right, now, the domain of our exponential function is the set of all real numbers. And this is very good to know. Again, hopefully this is an easy points for your homework and also when you take the exam. When we're looking at exponential functions, whether we shift them left, right, up, down, again, our domain will never change. It will always be this, all real numbers. Now the range will be the one that will change, and it depends on how the exponential function was moved or is behaving. Okay, so just one thing to know. Again, easy points on the domain. If you're asked that on the question, whether we shift it, move it, reflect it, the domain will always be the same, all real numbers. Okay. Now, the next thing that I like to do when we start exponential functions is give you this riddle. And when I have my face-to-face class, I tell them this is only a hypothetical situation. Okay, I'm not gonna give you guys $1 million, or I'm not gonna be giving you pennies every single day. But let me go through this riddle and then I'll explain why I go over it. So my riddle is this, or my proposition to my students is this. I tell them, suppose that on the first day of class, I give you 2 pennies, and every day for the next 31 days, I'll double your pennies. So I ask my students, would you prefer for me to give you this option, 2 pennies for 31 days, or would you prefer to have a lump sum of $1 million, right? And most of the time students think about it, right? And most of them think, oh, there's gotta be a trick, and they pick the pennies. But let's see what's going on here, okay? So this situation about me asking to give you 2 pennies on the first day and doubling them up for the next 31 days is this situation, right? That I have a base that is 2, which is I'm doubling, right? And my exponent is the days that are going to go by. So if I had a calculator and I calculated 2 to the 30th power, again, because the 2 to the 1 is just 2, right? So that doesn't really count. So if I'm looking at 31 days, I would put it on my calculator, 2 to the 30th power, right? So now if I plug it into my calculator, I have this very huge amount. But again, we're talking about pennies, so it's not to get excited just yet. So we need to move this into dollars, right? We're not wanting to see how many pennies we want, but we want this into dollars. So we move the decimal place 2 units to the left, and you see it's still a very big number, right? We have $10 million. So for those who chose the 2 pennies, you're getting $10 million compared to only the 1 million, that lump sum. And the reason why I like to start with this is just to show to you how fast an exponential function can grow. I mean, if we're talking about pennies, and in 30 days or 31 days, we grew those 2 pennies just by doubling them every single day to $10 million. I hope you see that these types of functions grow really fast, and they're very dangerous for that reason. And the main point that I want to point out to you is that when you are doing homework problems that involve exponential problems, um, you should not round your answers until you're done with all the operations, because as you can see, if 2 pennies, after a couple of days, we're talking about hundreds of dollars being added. So that's the same thing with your homework. If you round or shorten the answers as you go, the final answer can be off by millions, and you can be way off as far as what the answer is. Again, you're inputting answers on the computer, and the computer wants the exact answer. So please do not round when working with exponential functions until the end, okay? Because of this reason. All right. So this riddle that I just proposed to you or explained to you is basically this function, f of x is equal to 2 to the x. Now, I like to say that this is my parent function, that from this particular function, we model every single exponential equation or every single exponential problem, okay? So let's go ahead and take a look. So if we wanted to graph this, okay, this exponential function, we want to create a table, okay, just that's what we've done before. And I'm just going to do a random number of values for the x, okay, and they range from -4 to 2. So when I plug in -4 to my exponential function here, 2 to the -4, this is going to give me, yeah, the calculator is not going to recognize 2 to the -4, right? So we need to use our negative exponent rule of exponents to convert that to a positive. So this is 1 over 2 to the 4. 2 to the 4 is 16, so this is 1/16. So, and I do this for all my x inputs, and I get this graph, okay? So there's one thing, again, that we want to point out, okay? So we read these graphs from left to right. Our domain, if you see here, we don't see the arrow being pointed towards the left, and we don't see an arrow being pointed to the right, but our domain is all real numbers. And if we were to write this in interval notation, the answer would be from -infinity to +infinity, okay? And also, um, on this graph that you see here, exponential functions have what's called an asymptote. And in our class, we've been dealing with asymptotes when we saw rational functions. So I hope you fully understand now what an asymptote is. And when we're talking about asymptotes on a graph, remember this is an imaginary line where a graph cannot cross or touch. And again, in my face-to-face classes, I always like to joke, it's like in the city we live in, right? We're border town to Mexico, so we have this imaginary boundary line that separates these two countries, right? So um, we have an asymptote, and the equation of our asymptote for this parent function is y equals 0. We have imaginary horizontal line, and again, when we represent them, when we're graphing these, we graph these as a dashed line. Now, again, you can't see it because it's on the x-axis, okay? And then our range for this exponential function is all numbers from 0, not including 0, to infinity, right? So again, we don't include 0 because our graph will come very, very close to our asymptote, but never cross or touch it. Okay. So again, these are our basic properties, okay? All graphs will have a y-intercept at 0, 1, okay? Unless we do an alteration to our graph, either we shift it left, right, or up and down, our y-intercept will change. But this is in reference to our parent function or our generic function, yes? Then all graphs are a continuous curve. They have no holes, no jumps, okay? The x-axis is a horizontal asymptote that I just explained. And when a is greater than 1, then we see that our graph is increasing, right? When we read the graph from left to right, our graph is increasing. If we see that a is between 0 and 1, meaning it's a fraction, then we know that our graph is decreasing. It has a reflection on the y-axis, and we'll see an example of this. Okay. All right, so let's look at again our generic function or our parent function. y is equal to a to the x. So when we graph this, again, our domain in interval notation is from negative infinity to positive infinity. Our range is from 0 to infinity. Again, the way we represent that it starts at 0 but not including 0 is by using the parentheses. Bracket means that it includes it, so we don't want to use a bracket here. Our y-intercept is at 0, 1. Again, our graph is increasing, and we have a horizontal asymptote on the x-axis. And the equation of the horizontal axis would be y equals 0. Okay? And it's continuous. There's no gaps or holes in our graph. All right. So one of the things that I also want to point out is this, that when we have an exponent, a negative exponent, again, we can rewrite this using our negative exponent rule, that we take the reciprocal of the number and then we lose the sign, right? We change the sign of the exponent to a positive or vice versa. We had a fraction, convert it back to um, take the reciprocal, we give back the negative. Yes, so 2 to the negative x is the same thing or equal to 1 over 2 to the positive x. And this is what we say that our graph now is decreasing. It has a reflection on the y-axis, so instead of going forward, now it's going the opposite direction, right? And again, the domain is never going to change on our exponential functions. It's from negative infinity to positive infinity. On this particular problem, our range did not change as well. It's from 0 to infinity. Again, our y-intercept did not change either. It's 0, 1, but this one is decreasing, okay? The x-axis is still our horizontal asymptote, and again, our exponential function will always be continuous. There will be never any gaps or holes in our graph, okay? Again, if you have any questions, please stop me, ask me, um, or put them in the chat, okay? So you can get a sense of other exponential functions. What if we change the base, right? What if we change the base instead of 2 at 3? How will this affect our graph? So again, to look at it into practice, let's go ahead and build a table, okay? And if we do this table and pick certain numbers, okay, we plot these points on our graph, and using a better graph, this is from our calculator, what we see is we see this graph. Now, if I were to graph that previous function, our parent function, okay, our graph would be very similar. It would still go through the y-intercept at 0, 1, but our graph would be a little bit wider. So the higher the base, the faster the exponential function will grow. And one of the things that I mentioned to my students is like, okay, if 2 pennies in 31 days gave you $10 million, then what would 3 pennies and doubling them every day would give you? A much higher number, right? So the higher the base, the thinner the curve is going to be. It's going to shoot up a lot faster. It's going to increase a lot faster, okay? So let's look at the inverse, right? Or the opposite, right? So we have a base 4, but we have a negative x. Again, we have a reflection on the graph on our y-axis. And again, as you can see, if you can compare it to our previous graph, this curve is a lot steeper. It's going a lot faster. Again, all of these different functions that I gave you, I've only been changing the base. So I really haven't been changing, I haven't been moving this graph either left, right, up, or down. So nothing has been changing. My y-intercept still stays the same at 0, 1. My domain, again, will never change. It's always from negative infinity to positive infinity. And my horizontal axis is, asymptote, excuse me, is still the x-axis, which is y equals 0, okay? All right, so let's look at some properties before we get into working with more exponential functions. Let's review, okay? And hopefully, I believe all of you already know these properties, but again, it's always good to review. So let's first look at our exponent laws. Let's look first at our product rule, okay? That says that when you have two exponents that have the same base and they're being multiplied to each other, you're going to add the exponents, okay? So opposite to that, there's division. If I have two exponents that have the same base and I'm being divided by them, I'm going to subtract the exponents. The power rule says that if I have an exponent and I take that to another exponent, then I'm going to multiply the exponents together, okay? And the same thing here, we distribute. It's still the power rule. We have to distribute the x to all of our values or bases inside the parentheses, okay? Um, and same thing here. This is the power rule for a product and the power rule for a division, right? If I have a fraction into an exponent, I have to apply that exponent both to the numerator and to the denominator, okay? Now, x can never be equal to 0, okay? And um, just to review, anything to the 0 power, our answer will always be 1, okay? I can have x to the 0, the answer is 1. A million to the 0 power, the answer will always be 1. Anything to the 0 power, it's always 1, okay? Now, this here is called our one-to-one property or rule that says that if I have an exponent of base a to some exponent x, it's equal to some other exponent to base b, exponent x, these two exponential or functions or equations can only be equal if a and b are equal and if x and y are equal, right? So it makes sense, right? For these two exponents to be the same, the base have to be the same, and the exponents have to be the same for them to be equal. And again, this is what's called our one-to-one property. All right, so I had mentioned to you the one-to-one property. This property, we'll use it a lot, and it's useful to solve equations whenever we're trying to solve um, an exponent value based on an equation. Okay, so let's go ahead and look at an example. So you have a homework problem that says solve the given equation for x, and I have an exponential function on the left that has a base 10, and my exponent is 2 minus 4x equal to another exponential function that also has the same base, 10 to the 6x minus 1. So this is a clear example that I can use using my one-to-one property, because both of these um, exponents, both on the left and right, have the same base. They're both base 10. So for these two to be equal, then that means the exponents have to be equal. That means that 2 minus 4x has to be equal to 6x minus 1. And this becomes just an algebra to solve for x. I'm going to move everything that has an x to one side and just the numbers or the constants to the other side, right? So here I subtracted 6x on both sides. I subtracted 2 on both sides because I like the variable on the left. So I have 2 minus 2 is 0, minus 4x minus 6x is minus 10x. 6x minus 6x is 0, they canceled, and minus 1 minus 2 is a minus 3. So to solve for x, I'm going to divide by a negative 10 on both sides. And a negative divided by a negative is a positive, and this gives me 3 over 10. So I was able to use my one-to-one property to solve for x given two exponential functions. Okay, questions? No questions, good. All right, so let's try this one. This one's not so obvious, right? Can we use the one-to-one property for this equation? Well, I think so. So the trick would be is that the right side has to have the same base as the other side. So one of the things that I can do is if you don't see this, I went ahead and wrote here 4 to the third power is 64. But what I tell my students, especially for big numbers, okay, if you don't see it, what I would recommend is you all do a what's called a factor tree, or a prime factorization tree, right? So let me see if I can get my pen to work. I'm always having trouble with this new Blackboard. Okay. Okay. So what I do is I get 64, and since 64 is an even number, what I'm going to do is I'm going to divide this by 4, because I know 4 is an even number and I want the base of 4. So I'm going to do these divisions, right? I'm going to divide 4 into 64. So 4 will go into 6 one time, remainder 2. 4 will go into 24 6 times, okay? And then, so I have a 4 as a base, so 16. I'm going to do the same thing. Can I divide 16 into 4? The answer is yes. So 4 divided into 16 is, again, 4 times. So 4 times 4 is 16. So the factors, or the prime, or sorry, not the prime numbers, but the numbers that have a base 4 for 64 are 4 times 4 times 4. Okay, so here I have 3 4, so this is where I got the 3 from, 4 to the third. Okay, so again, this is a good thing to do. Again, it's part of the prime factorization tree that they showed you back a long time ago, but I can use it. These are not prime numbers. Again, that's why I had a slip of the tongue, but I use it to find my base 4 if I can convert 64 into something that has a base 4. All right, so now that I see that I can convert the right side to have a base 4, now I can apply my one-to-one property, because it states that if I have two exponential problems that have the same base, for these two exponential functions or equations to be equal, the exponents have to be equal. So that means that x plus 1 has to be equal to 3. So then the math is easy. Solve for x, subtract 1 on both sides, and we have 2, right? So 3 minus 1 is 2. So x is equal to 2. Okay. So again, our one-to-one property is always the one to go. And now also, by us representing or showing you these two sections, you'll see that we won't really need a calculator to solve most of our homework problems. Okay. That if we know these properties, that we know our rules and laws of exponents, we won't really use a calculator. Okay. All right, let's move on. So how about this one? This one's a little bit more complicated. And again, I'm going to show you, if I can get my pen to work. Um, you know, the 125. First, of course, before I change it, again, I just wrote it on here, but let me fill in some gaps on how I got from 1 over 125 to 5 to the negative 3. So the first thing I saw is 125. Okay, I know that I have to have this as a base of 5 for me to use my one-to-one property, so that's what I'm going to do. Can I get all the bases for 125 from 5? So let's try it. 5 divided into 12 will go in 2 times, remainder 2. So 5 will go into 25 5 times, right? Oh, then 25 is divisible by 5. So 5 will go into 25 5 times again. So again, 125 can be represented 5 times 5 times 5, or 5 cubed. But then again, I use my property or rule that I can convert this into a base by taking the reciprocal of 1 over 5 cubed, which gives me 5 cubed over 1, which is just 5 cubed. But again, I had to change the sign. Since the denominator was positive, then as a numerator, it's negative. Okay, so now I can see that I have two exponential problems that have the same base. So for these two to be equal to each other, then that means my exponents have to be equal. So I have x minus 3 should be equal to negative 3. Solve for x, add 3 on both sides, and it shows that x has to be equal to 0. Okay, and it's easy to see now. Now that we've done all this work, if we put here 0 minus 3, this is going to give me 5 to the negative 3. 5 to the third power, I know it's 120, or sorry, I have to take the negative exponent rule, which will give me 1 over 5 cubed, and 5 cubed is 125. Okay? But again, we're demonstrating our one-to-one property. Any questions? I hope you're loving, the one-to-one property. Again, I love it. It's my easy way to solve exponential functions. All right, let's do one more. Um, um, now, on this particular one, for those of you who see these later, make sure you answer the answer to get credit for the class. Okay. So we have 2 to the x plus 6 is equal to 8. Again, I won't do my, oops, I won't do my tree again, because hopefully you see that 2 to the third power gives me 8. 2 times 2 is 4. 4 times 2 is 8. So we have 2 to the third. And um, if we have 2 to the third, then that means both sides are equal to 2. So for these two to be equal to each other, x plus 6 has to be equal to 3. And so subtract 6 on both sides, you'll see that x will be equal to a negative 3. Okay? All right. Um, so let's look at the business side or the business of an exponential function, and we use the base e for these. Okay, so e is a symbol that represents a number, just like some of you might know pi, right? Pi equals 3.14 blah blah blah. It's a number that keeps on going. Well, same as e to the 1 power is represented by this number, 2.7182 blah blah blah. Okay, it's a number that never repeats, goes on. um, so this function, f of x is equal to e to the x, is called our natural exponential function. And let me tell you, the graph of this exponential function is the same as the one that we started with, the one that we drew at the beginning. F of x is equal to 2 to the x. It's the same exact graph, again, but we're using our natural exponential values. Okay? But it produces the identical graph. It still has a y-intercept at 0, 1. It has a horizontal asymptote at y equals 0. Again, you see it's increasing. The domain is from negative infinity to positive infinity. My range is from 0 to infinity, not including 0. And again, exponential functions do not have any gaps or holes in the graph. Okay? They're continuous. All right, so they have the same properties as we covered before. If I have e to the negative x, then this becomes a decreasing function, right? It has a reflection on the y-axis, okay? Again, the domain, whether we switch it, move it up, down, the domain will never change. Our range, again, for these two exponential equations are still 0 to infinity. So let's apply, again, our one-to-one property to a natural exponential equation. So we have this exponential equation, e to the x squared minus 3 is equal to e to the 2x. Again, these two have the same base. Their base is e. So my one-to-one property says that for these two exponential equations to be equal to each other, the exponents have to also be equal. So then that means that x squared minus 3 has to be equal to 2x. Okay, so this one's a little bit more tricky because we have an x squared. So what I'm going to do is I'm going to move everything to one side, and I'm going to move to the left side because it's the easiest path to go. I'd rather move one element to the left instead of two elements to the right. And if you notice here, by us having the x squared, we have what's a quadratic equation, right? So when I move this to one side, okay, um, what we can see is we can use several ways to solve it, right? You can factor it, you can use the quadratic equation. So there's several ways, right, for us to solve for it. Again, my way or my approach is always to factor. So that's what I'm going to do. So when I have x squared minus 2x minus 3 equals to 0, I say to myself, I need to find two numbers that when I multiply them together give me negative 3, and when I add them together gives me a negative 2. What are those two numbers? Well, that would be a negative 3 and a positive 1. Negative 3 times 1 gives me a negative 3. A negative 3 plus 1 gives me a negative 2. So those are my factors. That's how I would factor x minus 3 times x plus 1. And by me factoring, I can see what the values of x would be, right? X can either be 3 and x could either be negative 1, right? If you don't see it, you can solve for it. Add 3 on both sides, subtract 1 on both sides. So I was able to solve. Now, it's very important for you to always check your answers. Okay, so especially when you have two answers, plug them back into the original equation to see that both sides are equal to each other. Okay. All right. Moving on is I want to introduce the very famous compound interest formula. Okay, and this is a famous exponential formula, and I say famous or very popular because it's used a lot. I mean, if you have a bank account, the bank uses this formula to calculate how much interest to pay you. If you ever want to buy a car, this is the formula that a car dealership will use to calculate your payments that you'll make every month on your car. So let's review the formula in detail and look at these values. Okay, so first the A. Okay, again the A comes from an annuity, but the way that we like you guys to think of this A as the future value. Okay. Again, we're going to be talking about money, so going to give you a little bit more details on this too. But first, again, A, I want you to think of this as your future value. P stands for principal, but I want you to think of it as your present value. Again, there's a typo here. This shouldn't be future, it should be present value. Do apologize for that. R is our annual interest rate. And just like when you go to the stores, right? When they give you 20% off, 30% off, as you can see, they give you in a percent. But since we're going to be using a formula, it's very important that you convert that percent into a decimal. Okay, it's a very common mistake that I see students do, that they just put the 30 into the formula, and no, we need to change that into a decimal because they're giving our rate in a percent. And N represents the compounding periods. And we'll talk a little bit about those. There's several that represent N. And the last variable is T. T stands for time, and it's the number of years that we're going to be looking at our formula. Okay, so let's go ahead, and to better understand this, is go over our compounding periods. Okay, so whenever you see the word semi-annually or biannually, that means that your end value is equal to 2. Okay. Whenever you hear the word that your compound formula is being taken quarterly, well, the way I tell students to remember this is always, how many quarters are there in a dollar? 4. So our n would be equal to 4. Again, for those who probably have already purchased the car and have to make monthly payments, how often do you have to give a payment to your car? Well, it's 12 times a year, right? So n equals 12. You'll also be asked to calculate the compound interest formula daily. And the value you're going to use is 365. 365 days in a year, so n will be 365. Okay. Now, um, let's go ahead and work with an example. Okay, so this is an example of our compound interest formula, and it says, find the amount to which $1,500 will grow if deposited in a bank at 5.75% interest, compounded quarterly for 5 years. Okay, so before we write anything down, again, we want to make sure that we know what we're working with, right? When they say that they want to find the amount to which $1,500 will grow, that means that our $1,500 is our P, it's our present value. And we want to find out what our future value will be from applying an interest. So what we're finding or solving for is the A, right? The future value. So let's go ahead and write these down as far as we have. So we have P is the 1,500. We convert the percentage again into a decimal, and I just divide by 100 to move the decimal 2 places to the left. So we got 0.0575 as my rate. Again, you never want to round. When you're plugging these values into the calculator, make sure you use all these numbers. And this is what I was talking about. If you round, your answer will be very, very off. It'll be wrong, okay? Because again, exponential functions, 2 pennies will make a big difference, okay? Um, what do we also know? We know n. They said that the interest was going to be applied quarterly, so our n is equal to 4. And how long are we going to be looking at our our interest? For 5 years. So that's our time, t. Okay, so let's go ahead and plug it in to our formula. A equals p times 1 plus r over n times nt. Okay, so again, P is the 1,500, 1 plus our rate, which is 0.0575 divided by 4, and all of this is taken to 4 times 5. Okay, so 4 times 5 is 20. Didn't show all my work, but let me review. If you're doing this on a calculator, you always want to follow the order of operations. So since I have a parentheses, what I want to do first is what's inside the parentheses. So what I would be doing is I plug in my calculator, 0.0575 divided by 4, and then I'm going to add 1 because, again, you're going to do multiplication and division first, addition and subtraction last. Add the 1, take that to the 20th power, and then last, multiply that value to 1,500, and it's going to give me the $1,995.55. So this is another thing that I also want to point out, okay? We are dealing with money, okay? So money, when even though the problem didn't say how to round, because this problem, it was 5, 5, 4, 3, 2, blah, 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 it kept on going, okay? It didn't ask me to round, but again, because I'm dealing with money, the computer is going to expect that you round your answers to 2 decimal places, because that is sense, 2 decimals, okay? So another piece of advice and information. All right, so let's look at this other problem. It's a finance problem. So a couple just had a baby. How much would they invest now at 5.8% compounded daily in order to have $35,000 for the child's education 18 years from now, right? These parents wanna prepare for college, right? For their newborn baby. So they want to put this money into an account, and their account gives them a 5.8 interest. Let's see, what do we have? So the 5.8 is our rate, which is, we converted into decimal, 0.05, oops, this is a typo again. This should be 0.0580, okay? Our present value, or excuse me, our future value A is what we want to have, the $35,000. The time is 18, and then they said daily, right? So daily is at 365. So we're gonna plug it in. We're solving for our present value. We want P. What do we need to deposit now? So, oh, now it's correct. Okay, now I have the right rate here. Okay, so plugged it in. So I have my A is 35,000 equals to P times parentheses 1 plus 0.058 over 365, all this to the exponent 365 times 18, okay? Again, I order of operations. I'm going to do what's inside my parentheses first. I'm going to divide 0.058 by 365, gives me this number. I'm not going to round. This number that I wrote here is all the numbers that my calculator gave me. I don't want to round, okay? I'm going to add 1 to this. This gives me 1.00158,904, and 365 times 18 is 6570. Okay, I'm going to take this to this exponent, this number, to 6570. This is going to give me P times 2.840320963. Again, these are all the numbers that my calculator gave me. I'm not rounding. So to solve for P, I'm going to divide this number on both sides. Okay, so P is equal to 35,000 divided by 2.840320963, which is going to give me, again, $12,322.55. Again, I'm rounding to 2 decimal places because I am dealing with money. Okay, so I hope these equations help you solve for these word problems. Again, the key that I want to reiterate and stress is do not round. Okay, exponential functions grow really fast, so you never want to round your answers or they will be wrong. Okay. All right. So again, we just covered applications. The one thing that I also want to point out is that you'll also, on your homework, you're going to be asked to find a future value, or the A, for something that is going to be compounded continuously, and it's not this formula. Whenever you see this word continuous, you're going to use instead this formula. A is equal to PE to the RT. Okay, So let me see, I think I have an example for this, and I don't. So I don't have an example, but it would work the same. Again, R is still your rate, and T is the time. So one of the key factors that you're also dealing with a continuous compound interest formula is that they won't give you a compounding term. They won't say annually, quarterly, nothing like that, or daily. Okay, it's just gonna say continuous. Okay? So keep that in mind. It's this formula to answer for future value or present value. So let's go ahead and move into the logarithmic functions. Now, um, a lot of the students dislike these because again, you have to do a lot of manipulation for your calculator to do these problems. But I wanted to point out that a logarithmic function is the inverse of an exponential function. That like in mathematics, everything has its opposite. So logarithmic functions are opposites to inverse functions. And by knowing this, what we can do is, again, we have the same rules that apply to log functions that can help us solve these problems without using a calculator. So let's go ahead and review some of these rules or properties. And the first one that I want to start off with is my favorite one, the one-to-one property. Okay, and again, you'll see that you'll use this a lot, and it's very useful to solve logarithmic equations. And it's the same concept that we saw with exponential functions, that for two logs to be the same, okay, um, they 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 both have to have the same input. Okay, and I'll cover also a little bit on how we write logs. So let's just for right now review some of our rules and properties. Okay, so first of all, for a function, and we've covered this before, for a function to have an inverse, okay, we have to have passed these several tests, right? So one is our horizontal line test. Our vertical line test, if you guys remember, it was to test that it was a function. But to test if a function or equation has an inverse, we have to apply our horizontal line test. Okay, so keep that in mind, that we need to test for our horizontal line test to see if in fact it has an inverse. Okay. All right. So let's let's check this. If I have these two graphs, um, of these two graphs, are these functions one-to-one? And for them to be one-to-one, again, what that means is it has to pass both tests. It has to be a function, and it has to have an inverse. So first, we'll test if they're a function. The first one, yeah, it's a function. It passes my vertical line test. If I have an imaginary vertical line, my imaginary vertical line will cross my graph only once at each point. Same with B. If I do my imaginary vertical line, my imaginary vertical line will cross my graph only once. So it does pass the vertical line test. But what about my horizontal? Does it have an inverse? So if I do a imaginary vertical line for my A, I see that it does, right? It looks like it does pass my graph once. But what about my second graph, B? Does this pass the horizontal line test? Well, no, right? That you see that it'll cross at 2 points. So my B is not one-to-one because it does not pass these two tests. It does not have an inverse. Okay, so again, the definition of an inverse, it means that it has to be one-to-one. And again, for it to be one-to-one, it has to pass both the vertical and horizontal line test. Okay. Um, and we can interchange these values. And I'm going to show you how to find the inverse of a function first. Okay. So if the horizontal line test fails, it does not have an inverse. Okay? So let's look at this graph, our logarithmic function. So to get ready for our logarithmic function, let's review again what we just saw, our exponential function, which was its inverse, right? So here on our exponential function, we had a base of 2 to some exponent, okay? Now, for our log, okay, our log, we write log as log, okay? This is the math representation of the log, okay? If our exponential function had a base of 2, then our logarithmic function also has to have the same base, a base of x. Okay, um, And for these to be interchanged, again, we can change the values. The input of the x has to be the input of a log has to be the output of an exponent. The output of a log has to be the input of an exponent. So that's what we mean about interchanging the values, that we can find that one's an inverse of the other if we can interchange the variables. And we've seen inverses before also for linear equations. Okay, so as an example, on these two that I was just showing you, okay, you see here they're opposites of each other, right? So when x is equal to -3, we have our output as y over 8. But when I do the opposite, we have 1 over 8 is equal to -3, right? If I would interchange my outputs, they're opposites, right? So when, again, if my input was -2, my output was 1/4. For the logarithmic function, input is 1/4, my output is -2. Okay, so they're ordered pairs that are reversed for both equations or functions. All right, so graphically, again, you can see that the reflection is on a y equals x axis. Okay, this is my exponential function. Just so you can see that they're opposites. Again, my exponential functions have a y-intercept at 0, 1. My log functions have an x-intercept at 1, 0. My exponential functions have a horizontal asymptote at y equals 0. My logarithmic functions have a vertical asymptote at x equals 0. Okay, my domain of an exponential function is from -infinity to +infinity. Well, that's the range of a log function. The range is from -infinity to +infinity. The range of an exponential function was from 0 to infinity. Well, that's the domain of a log function. The domain of a, excuse me, the range of the domain of a log function is from 0 to +infinity. Okay, so they're opposites of each other. They're inverses. All right, so let's review again what everything that I just said. Okay, so these are the domains. As you see, they're opposites, and then the range are opposites. This has a y-intercept, this has an x-intercept at 1 and 1. The horizontal asymptote for the exponential is the x-axis. The log function has a vertical asymptote at the y-axis. Okay, all right, so let's go ahead and look at some examples of using our one-to-one or converting from a log to an exponent, which will come in very handy again for us not to use a calculator. Okay, so here, one thing that I also want to point out, just as we had a natural exponent, we also have a natural log, and the symbol for the natural log is ln. Okay, these are equal to each other. Ln of log of e to the x are equal to each other. Also, one thing to point out, that on your computer, whenever you see a log with no base or no number or subscript, that automatically we assume that we are dealing with base 10, and that's the base that your calculator can do. If we are looking at a log that's not a base 10, then again, your calculator has to do you have to do a little bit of math in order to be able to calculate it. All right, so let's go ahead and do a conversion from log to exponents to see that we don't really need a calculator to solve these logs. Okay, so if I have a log of base 4 and my input is 16 and my output is x, okay, I can convert this into an exponent. So my log has a base 4, so my exponent has to have also a base 4. So here, my base for my exponent is 4. Okay, again, the input of the log becomes the output of the exponent, and the output of the log is the input of the exponent. So 4 to the x is equal to 16. And I can see that I can rewrite this as, to use my one-to-one, I can rewrite 16 as an exponent. That is 4 squared. So for these two to be equal, x has to be equal to 2. Okay, so hopefully you see that logs are not that complicated if we know our properties and we know that it's an inverse to an exponent, because we can calculate any um, exponent, right? How about this one? Let's do the opposite. I have an exponential problem. 5 cubed is equal to 125. Let's convert this into a log. So I have my exponent as a base 5. So I'll convert my log to base 5. The input of the exponent becomes the output of the log. The output of the exponent becomes my input of the log. So this log of base 5, input 125, my answer would be 3. Okay. So let me run through these quickly. Again, when they don't give me a base, I can rewrite this. My exponent base will just be b. My exponent will be the output of the log, which is 3, and the output is the input of the log, which is 27. Okay, so these examples are to convert from logarithmic into exponential or vice versa. Okay, all right. Um, so how about this one? I like to always show this one to show that the square root can be represented as an exponent. Okay, so first, okay, I rewrite the square root of 81 to 81 to the 1/2 power. Okay, so square root can be represented as an exponent of a half. Okay, so we have 81 to the 1/2 is equal to 9. So I know that my log will have a base of 81. So log of 81, my input would be 9 equals to 1/2. Okay. All right. So cover the properties of logs. I'm going to run out of time. So here we have the log of base a is equal to 1. So remember on the exponent, when we had anything to the input of 0, the answer was 1. Well, now when we input a 1 to a log, our answer will always be 0. So this is one to remember, okay? Whenever we have a log of any base, it doesn't matter what the base is, the input is 1, our output will always be 0. So this one's called our one-to-one property. We have a log of base a, and when input a, this will be 1, and this is like the identity of our exponent. When we have a to the 1, the answer is just a. Okay, this is our power rule, that if we have a log and we have it to the exponent, well, we just multiply that exponent to the log. And again, a divided by a is 1, is our identity, so 1 times x is just x. And then this is the one that I like, the one-to-one property, that for log of a, base a of x equal to the log of base a of y, for these two logs to be equal to each other, my inputs have to be equal to each other. So let's go ahead and use our properties to solve this one. Log of base 3 of 1 over 27. So you'll see that I'm not going to use a calculator to solve. The first thing that I'm going to do is I'm going to convert that 27 to an exponent. So we have 27, so I know that I can convert that into 3 to the negative 3, or 3 to the 3 will give me 27. Again, use my negative exponent rule, will be 3 to the negative 3. So here, by plugging it in to my log, okay, this will give me, if I can convert this to log of base 3 of 3 to the negative 3, again, my answer is that power rule, right? The negative 3. Okay, I'm going a little quick. This session will be recorded so you can go back and review it, okay? So these are more properties of our logs to help us solve for equations. So let's look at this one. This is an example that we can use our one-to-one property, right? If I have the log of 3 of 1 over 27 equals to log of 3 of 1 over 3 cubed, for these two logs to be the same, again, this is our one-to-one property, right? That the inputs have to be the same. Okay? So let's go ahead, and I want to do an example because these are pretty much self-explanatory from the graphs or from the slides. Let me use one where we have to solve. Let me go forward. All right, let's do this one, solving an equation. So use the definitions of logarithms so you can solve the given problem. So we have log of base b, and my input is 1,000 is equal to 3. So what I'm trying to solve for is what's the base of this, right? So what I would do is, let me go ahead and convert it to an exponential problem. So I have b is the base, my exponent is the output of the log, which is 3, my input of the log is 1,000. So if I wanted to find the base that taken to the third power gives me 1,000, well, we can say that 10 to the third power, I know that gives me 1,000, so my base is 10. B is equal to 10. Okay? So again, converting it to a log to an exponent, we can either solve the exponent or solve the base by doing this conversion. Okay? All right, let's look at another example. Log of base 6 of input x is equal to 5. Again, they're giving us the base on this one, but what I want to know is what input gives me 5. So let me go ahead and again convert this log into an exponent. So I have my base is 6, my exponent is the output of the log is to the 5, and the output of the exponent was the input of the log. So 6 to the 5th power is x, so I can use my calculator to do that. 6 to the 5th power is going to give me 7,776 is equal to x, right? So on this one, I had to use my calculator because, all right, because this was a big number to calculate by hand, right? So again, if we can convert a log to an exponent, we can solve any exponent. And again, these problems shouldn't be that difficult. All right, so again, reviewing a little bit more properties, okay? 5, 6, 7, and 8, I'm gonna run through them quickly. Okay, when I have a log and my input, I see that is a multiplication of numbers or items. Okay, I can expand this to 2 logs, and this is again, this is the power rule that says that when I have a product inside of a log, I can separate that by the log of the same base b of m plus the log of the same base b of n. Okay, I have the quotient rule that if I have 2 items that are being divided by each other, I can expand these by subtracting the logs. The log of base b of the numerator subtracted the log of base b of the numerator. Okay, power rule, and then also our inverse rule, right? So let's do a quick example. This will probably be my last example. So solve for x given log of base 5 of x plus 1 is equal to log of base 5 of 9. On this one, I'm going to use my one-to-one property. Since they both have the same base of log, then that means that the inputs have to be the same. So for these two logs to be equal to each other, I'm going to use my one-to-one property. And this says that x plus 1 has to be equal to 9. Solve for x, subtract 1 on both sides. X is equal to 8. Okay, so the slides for this presentation will be uploaded. You'll be able to see all the others that I didn't get to. If you have any questions, I encourage you to stick around. We have awesome tutors. Visit the tutoring centers for help. Again, we started this section this week. Hopefully this helps you with your homework. Again, thank you for joining us today. We hope to see you again next Friday. Thank you so much.
Thank you, Mr. Carizales, for your wonderful presentation. I'll be stopping the recording now, but we do want to remind you about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and another short survey to receive credit for attending. Thank you all for coming in today. We hope you have a lovely weekend, and thank you again, Mr. Carizales, for the presentation. If you have any questions, feel free to use the chat box or your mic.